Hello. Now let us go to the next part of construction of the phase plane trajectory. So today we will see the delta method for the construction of the phase plane trajectory. Okay. This method in fact is used for systems, for any kind of systems which can be written in this form, in a peculiar form. Like for example, I write it down. If x double dot plus f of x comma x dot comma t equal to 0. That means we should have the function, we should have the differential equation uh, in this form. Then only it is possible to construct the phase plane trajectory using the delta method. Okay, and this function f of x comma x dot comma t can be a linear or a nonlinear function also, and in fact this can also be a time varying function. But the only thing is that it should be a continuous function as well as a single valued function. Okay, and now let us, if I will tell you what this kind of a function, I will give you an example of of this kind of a function. For example, we know the general form of the second order system 2 zeta omega n into x dot plus omega n squared into x equal to 0. So this is in fact f of x comma x dot comma t. Okay, so this equation can be written in this form. So I can apply the delta method for this kind of an equation. But we have to modify this equation to a particular form so that I can apply the delta method. Okay. So it is usually, the modified version is in this form. We usually write it like this. Okay. Omega n squared into 1 plus delta into x comma x dot comma t. So what would be delta then? So this is x actually, x plus delta, omega n squared into x plus delta. So omega n is nothing but the natural, undamped natural frequency of the system. So x plus delta means delta will be a function of 2 zeta and x dot right here in this case. So I can 2 zeta and omega n and x dot in this case. So we will try to expand this and see. This is nothing but x double dot plus omega n squared into x plus omega n squared into delta of x comma x dot comma t. So that means this part is equivalent to 2 zeta omega n into x dot. Okay, so only thing is this delta would be equal to omega n. This is omega n squared, right? We have to divide it by omega n, 2 zeta x dot by omega n. So that is what delta would be. So delta x comma x dot comma zeta would be equal to 2 zeta x dot by omega n. So this is how we represent this equation to apply the delta method. So in general, we can write it for a delta method in general. In order to use this kind of a method, the any system equation should be written, could be, have to be written in this form, omega n squared into x plus delta. So I have not written it as a function of x dot plus t equal to 0. Okay, right. So this omega n squared can be replaced with some k. So in order to make it as a general form. So, but I am replacing, writing it with omega n, where omega n is the undamped natural frequency of the system. Okay. So now we will choose the state variables for the system. X1 is equal to, here a little bit difference is there in choosing the state variables. X1 is equal to x, and X2, instead of taking x dot, we take it as x dot by omega n, in order to get it in a particular form. So we get x1 dot would be, x1 dot is x dot, right? X1 dot is x dot, but x dot is not x2. X dot is omega n times x2. So I have to write here it as omega n times x2. So what is x2 dot? x2 dot is equal to x dot x double dot by omega n. X double dot by omega n means, that is x double dot by omega n means x double dot is minus omega n squared into x plus delta. So this becomes divided by omega n will give minus omega n into x plus delta, right? So it is minus omega n. Instead of writing it as x plus delta, we will write it as x1 plus, sorry, plus delta. So what would be the slope of this kind of a system? What is the slope? Slope can be written as dx2 by dx1 is nothing but omega n into x1 plus delta divided by omega n into x2. So we have minus of x1 plus delta divided by x2. Okay, right. So now this is in fact the slope of the system at any point on in space for depending upon the value of x1 and x2. And here also delta is also a function of x1 and x2, right? Because it has here in this case, for this case, delta is a function of x2. In fact, x2 by x dot by omega n is there, so delta is a function of x2 directly. So depending upon the value of x1, x2 and x2, we can mark the slopes of the system at different points on the x1 x2 plane. So that is the idea, that is what we are going to try it now. In the case of the delta method, what we are going to try it is we are going to find out delta at different points on the plane. Delta at different point on the plane, x1, x2 plane, and using this delta and using arcs, we will use arcs to draw the phase plane trajectory. So in order to proceed in that way, so we will see what to do. So this, what we have to understand is this minus of x1 plus delta by x2 is the, suppose I have some trajectory on the x1, x2 plane. Sorry, this is one trajectory on the x1, x2 plane. The slope of this trajectory at any point will have the value minus x1 plus delta divided by x2. At any point, the slope value is minus x1 plus delta divided by x2. Okay, that is what we are going to use here. Okay. Okay, so we'll go to the next slide. So the idea, so how to plot this curve, we'll see what is delta, what is the advantage of this delta function here. So let me draw the x1, x2 curve here. This is, sorry, this is the x1, x2 plane here. So let us consider some point P on the x1, x2 plane where the point P is part of this trajectory, is somewhere on this trajectory. Let this be point P. Actually, this is somewhere on the trajectory. So the slope of point P, that means the slope at point P should be equal to, what should be the slope equal to be? The slope of this at the point P along the trajectory should be equal to, that slope should be equal to minus x1 plus delta divided by x2. Okay, so I have written with this with a different small color so that this we should come to that after some time. Okay, so we'll forget this part now. So we will try to mark this the points of P, the coordinates of P. So P is at a distance of x1, let it be at a distance of x1, 0 and x2, 0 in the x1, x2 plane. So let us consider this equation x1 plus delta and x2. Okay, x1 plus delta and x2. So at this point, what would be the values of x1 and x2? So it would be x1 0 and x2 0, and delta would be a function of x10 and x20, right, at this point. So I can calculate these values at the point P. So at point P, I will get these values, the corresponding values of x1 plus delta and x2. Okay, so what is x10 plus delta? It is some distance, right? x10 plus delta. I'm going to mark that value correspondingly. I'll move or push a little bit to the left and see mark delta here. And this distance is x10. So I have got the total distance x10 plus delta right here. So this total distance is x10 plus delta, and this height is x20. Okay, this height is x20, right? So if I draw a line from this point O to P, this. If I mark a line from point O to P, what happens is that it is a slope. What would be the slope of this line OP? So I can write the slope of this line OP. The slope of the line OP is, what will be the slope of this line OP? It is dx2 by dx1. What is dx2? It is x20. X2 0 divided by x10 by delta. So I can, in general, I can write it as x2 divided by x1 plus delta, right? x2 divided by x1 plus delta. So in general, at any point, if I move this point anywhere, I can call this point as x2 divided by x1 plus delta. So it is in fact the negative of the slope that we want of this line. So now we will what we are aiming at, we want to find out the slope of this line, right? We don't know the slope. Okay, where this, we only know that the slope is x1 plus delta by x2. So now if we look clearly at this line, and we will try to mark a perpendicular in this line. That means we will mark a perpendicular. This angle is theta. So this angle is theta. This is theta, right? It is in the positive direction. So this is nothing but tan theta, right? This is tan theta. Tan theta. Now if I mark a perpendicular to this line, so if this is a perpendicular, this is a perpendicular to this line, perpendicular to this line. So I will try to extend this line a little bit. I'll put dotted marks for extension of this line. This is, I have extended this line, and if I take this part, what is this angle? This angle is also theta, right? This angle is also theta. So what are we trying to find out? We are trying to find out this angle. We are trying to find out this angle, which in fact is the slope. I will write the slope as alpha. We are trying to find out this angle, which is the slope of this, the actual trajectory. Okay, so this is actually tan alpha. Tan alpha. So this, the total angle is 90. This total angle is 90. So what would be alpha? Alpha would be 90 minus theta, right? So alpha would be 90 minus theta. So I got this relation right directly. So alpha is 90 minus theta, right? 90 minus theta. So what would be tan 90 minus theta? Tan 90 minus theta is in fact cot theta. So it would be x1 plus delta by x2, right? x1 plus delta by x2. So here one difference is there. This line is going towards going upwards, whereas this line is going, we are taking it in the downward direction. So we have to put in a negative also to that value. So what would be alpha here? So what would be the slope of this line? The slope of this line would naturally be the slope of the line I will write it as xq, which is our trajectory. Xq is our trajectory. Trajectory is the slope of our trajectory, or in fact a part of our trajectory, which is proceeding in the direction of the slope of the trajectory, or xq is our trajectory. And what is the slope of it? What is the slope of it? So I can write it as xq slope is equal to tan of 90 minus theta in the negative direction, in the opposite direction as this line. Okay, so that means what is tan 90 minus theta is, so it would be minus of x1 plus delta divided by x2. So this is the beauty of this delta function. So in order to draw the trajectory, in order to proceed in the direction of the trajectory, the only thing that we have to know is along. So if we have an initial point P on the trajectory, what we have to do is we have to find out delta at that point, and then mark, if delta is positive, mark delta towards the left of x1, and then mark it as a point O there. Mark it as some point on the x1 x2 plane. Okay, then what we have to do is we have to, in order to mark a perpendicular, to draw a perpendicular to any line, what we have to do is we have to draw an arc with, we have to take the radius as O and P, and center with radius OP and center O, we have to draw an arc here. An arc is effectively a short arc is effectively a perpendicular to this line. Okay, so XQ is in fact the arc drawn with O as center and OP as the radius. So we will get that part of a very small part of the trajectory using this delta here. Once I move a little bit, we have reached somewhere near to Q. So I will now mark the new point as Q. Our new point is Q. So with Q, at Q, I have the new coordinates x10 and x20. I have got new coordinates x10. I got at Q. I got new coordinates x10. Again, x11 and x21. I got the new coordinates, right? x21. New coordinates. With the new coordinates, I would find out the new delta. So I would find out the new delta. The delta would be somewhere here. Then I will draw the line here, join these two lines. It is not necessary to join these two lines. Only thing is that we have to mark this point, new delta, and with delta comma 0 as the center, and this point, let me call this as O dash. O dash Q as the radius, draw another arc. Okay, so from this line, we have to draw a very short arc again. So we got another small arc here. So we are proceeding in the direction of the trajectory. We got another arc, which is also in fact the slope at this point. Then we will move a little bit shorter distance further. Then again we will find the new coordinate points x12 and x22. Like that we will go forward and then plot the trajectory. This is the idea of the delta method. Okay. So now we will try to do a problem based on this method. Okay. So let us consider, we can even do the nonlinear method on the symbol system. You can try out this system. I will give you that symbol equation. Try out the system. Try out the delta method on x double dot plus 2 zeta omega n into x dot plus omega n squared into x equal to 0. This we can easily make it in terms of omega. So we will try to, now do a system with a nonlinear damping. Okay, instead of this linear damping, we will go and look at a system with a nonlinear damping. So we will see that equation. So we will see the problem here. We'll consider the system x double dot plus 4 modulus of x dot into x dot plus 4x equal to 0. Okay, we have this kind of an equation. So how will you write this equation? So I can write this equation in the form x double dot plus, let me take omega n as equal to 2. So here what would be the omega value of omega n? Omega n is equal to 2. I can write this as 2 squared into x plus delta. So what would be delta here? So delta will be a function of this part, right? Delta is a function of this part. So I can write this as delta. If you find out delta, delta would be, this is 4 x dot modulus of x dot into x dot divided by 2 squared, right? So it is in fact 4 and 4 gets cancelled. What remains is x dot and modulus of x dot. So it becomes x dot into x dot. Okay, so I have got this. Okay, so now let us choose the state variables. X1 is equal to x and x2 equal to x dot by omega n. So it becomes 2. So we have x1 dot is equal to omega n to x2 and x2 dot is equal to 2 into minus 2 into x1 plus delta. Right, we have the same set of equation. Okay, so what is delta in terms of the state variables? So what would be delta in terms of the state variables here? Here, if I represent delta in terms of the state variables, I can write it as delta, where delta is equal to x dot by 2, right? X dot by 2. So x dot is equal to 2 times x2, and x dot modulus is positive, right? We have taken the absolute value. Since 2 is again positive, I have 2 times of 2. So it would be 4 of x2 dot x2 into x2. Okay, so where delta is of this form, dot is not there. So I made a mistake here, dot is not here. Okay, fine. That's it. So now we have been given the initial point as 1 comma 0. Let the initial point be 1 comma. The initial conditions of the system are given. Initial conditions are given. That is 1 comma 0. So we will start from 1 comma 0 and see how the trajectory looks like. Okay. So we will start here with okay, so I will take the initial point somewhere here, because I will take a far away point here, because taking the arcs is quite difficult. I have to show here like how we are going to proceed. So this point, let me take it as 1.1. Okay, this is the x1 axis. This is x1 and this is x2. X2. Okay, so this is point 1. So at point 1, I have point 1. What would be the values? It is x1 is equal to 1 and x2 equal to 0. So what would be delta at that point? Delta would be 4 into x2. x2 is 0. 0 into 0, it is 0. So delta is 0. So I have this x1 here, delta is 0. So what would be the delta point? Delta point would be the center here. So I have the delta point here. I will mark the deltas with orange color. This is the first point of delta. So I can write O1. I will call it as O1. The center point as O1. So with O1 as center and radius as 1, I should draw an initial arc for the system. Okay. The initial arcs I will draw with this pink color. So the arc I will draw with this, and I will move a little bit forward. Okay. So this has to be an arc, but it didn't come out perfectly. So it is a small arc. Okay, so I have moved a little bit towards the right. Okay, down, towards down. So I got a new value of x1 and a new value of x2. Right, it is something very small value, because this length I had taken it as 1, and this would be somewhere here as 1. So it would be some point 1 or point 1 or something. Let us assume it as some point 1. Let us assume it as some point 1 here. The new point, I got it as 2. At 2, so here we need to consider only x2, because delta is a function of only x2. Okay, delta is only a function of x2. So I got the new point 2. Second point. At 2, what would be the values of delta? At point 2, at point 2, so I got the values at 1 and 2. So what would be the value at this point? X2 value, let it be equal to zero point 0.1. At this value, the value of x2, let it be equal to zero point 0.1. So let it be equal to zero point 0.1. So it is minus zero point 0.1. So what at 2x1, I'm not bothered what would be the value. It is something 0.9 or something. X1 is equal to some 0.98 or something like that. So x2 is, let it be 0.1, minus 0.1. So what would be delta of x2? 4 times magnitude of zero point 0.1, magnitude of minus zero point 0.1 into minus zero point 0.1, right? So it is nothing but zero point 0.1 into minus of zero point 0.1, it is minus 0.01. Okay, so here I got a negative delta. Negative delta means I have to move towards on the right of the x-axis. Okay, x1 axis. If it is a positive delta, I have to move towards the left of the x-axis. Okay, left of this x2 axis. If it is negative delta, I have to move towards the right. Okay, because I am decreasing x1 plus delta means x1 minus delta. Okay, because of this negative sign. So that means I have to subtract it. That is why I am moving towards the right. So I got a new point minus 0.01. So delta would be 0.01. So I have to move a little bit further here. So my new delta would be O2 would be here, right? So with O2 as center and O2 2 as a radius, this as a radius, I have to draw a new arc now. So I have to draw a new arc now. Okay, I have drawn a new arc here. So I will draw a new arc here. So I reach another point here, third point. So similarly, I have to move forward. So when I'm at point 3, I will get at point 3, I will get a new delta. I will move to another point. I will get a new delta O3. So when I'm at O3, what I will do again with O3 as center and O33 as a radius, I will draw another arc here. In that way, I will go forward and find out all my points here. When I move forward, what I get, but we have to move with short distances so that I will get more accurate results. So I will get as many deltas as here. If at any point of the time, if I get a positive delta, I move towards the left of the x2 axis. I have to move the center point of delta will be shifting. So delta points will be shifting here so that I can move around with this. So I will move like this. So it would be something which is moving like this, and it may come to 0. This is how we draw. It is in fact short arcs. We are drawing the short arcs to find the new points. Okay. This is how we move forward using the delta method, and we will come to the in fact come to the equilibrium point. So these O1, O2, O3s will be shifting. Okay, O4, O5, like that. Okay, like that it will be shifting. But when it comes, when I cross this point, what happens here at this point? Delta becomes positive. When, because x2 is positive here, delta becomes positive. When I come here, I will be shifting to this point. I will be shifting towards the left. So that is the difference here. Okay. So this is about the delta method. It's a very simple method, but we have to take move in small steps in order to plot the trajectory. Okay, you can try out this problem for this system. It's for the simple system, and see whether you are getting the curve of for the system. Okay. Okay, so I will give some problems based on this. Okay, so this is about the construction of phase trajectory. So we have completed the portion on construction of phase trajectory using the graphical methods. Okay. Now we will go to a very interesting topic in nonlinear systems, which is the stability of nonlinear system, and we will we will try to understand a very powerful method in analyzing nonlinear system, which is the Lyapunov method. Okay. Okay. Thank you.